What is it about puzzles that makes them so engrossing? Imagine you're going about your day, thinking your very practical and familiar thoughts, when suddenly someone challenges you to measure an interval of 9 minutes using only a 4-minute hourglass and a 7-minute hourglass. You're dismissive, perhaps, protesting that you have no time for such things. But the question gnaws at you. It keeps coming back to you throughout the day. How do I measure 9 minutes with only a 4-minute hourglass and a 7-minute hourglass? At some point, you think of asking what happens if you start both hourglasses going at the same time. When the 4-minute glass runs out, the 7-minute glass will still have 3 minutes to go. That means we can readily measure intervals of 4 and 7 minutes by using each hourglass individually, or 3 minutes by using the remaining sand in the 7-minute hourglass after the 4-minute hourglass runs out. But how does that help you get to 9? And suddenly, all of your very practical thoughts are gone. They're banished until you solve the problem. Or maybe instead I tell you about my friend Steve. He's a waiter at a restaurant, and he's very good at his job. One day, he was serving 4 people, and he asked, "Do all of you want coffee?" The first one said, "I don't know." Then the second one said, "I don't know." Then the third one said, "I don't know." And finally, the fourth person said, "No." Somehow, Steve then knew exactly who wanted coffee and who didn't. Can you do the same? Who wanted coffee and who did not? So I repeat the question. What is it about puzzles that makes them so engrossing? The French philosopher and statesman Joseph de Maistre, writing in the 18th century, observed that it is one of man's curious idiosyncrasies to create difficulties solely for the pleasure of resolving them. It's unclear why this is. In his book, The Puzzle Instinct, anthropologist Marcel Danesi wrote, "Why have people from time immemorial been so fascinated by seemingly trivial posers, which nonetheless require substantial time and mental effort to solve, for no apparent reward other than the simple satisfaction of solving them? Is there a puzzle instinct in the human species, developed and refined by the forces of natural selection for some survival function? Or is this instinctual love of puzzles the product of some metaphysical force buried deep within the psyche, impelling people to behave in ways that defy rational explanation?" Personally, I wouldn't be surprised if Danesi's first suggestion is right. Maybe evolution favored those of our distant ancestors who were better able to solve puzzles, and that led to our modern taste for them. But whatever the explanation, it's certainly true that it's hard to shake off a good puzzle. I'll bet that you've been mentally flipping hourglasses for the last few minutes. Or perhaps you've been wondering how Steve knew who wanted coffee. Don't worry, I'll give the solutions to both puzzles and the solutions to all the other puzzles I'm about to present at the end of this lesson. For now, though, here's another puzzle. 2 roommates were arguing over who should clean the kitchen. They decided to flip a coin to determine who has to do it. But it turns out that the only coin they have is actually biased. Instead of the coin being 50-50 between heads and tails, this coin lands heads 60% of the time and tails just 40% of the time. The puzzle is this. How can they use this biased coin so that they each still have a 50-50 chance of having to clean the kitchen? How do you solve that one? But perhaps you're wondering what any of this has to do with mathematics. I've already presented 3 puzzles, but none of them seems to have anything to do with math. The one with the hourglasses involves a few numbers, but that's about it. I've shown you no equations, no bizarre symbols or strange jargon. Nothing, frankly, that a middle school student would find hard to understand. This is not mathematics as most people understand that term. Ask most people about mathematics, and they will give you a shudder. They'll think of the tedious algorithms of arithmetic and the stress of algebra and of being expected to follow incomprehensible rules about manipulating meaningless symbols to solve pointless problems. But that's not how mathematicians view things at all. For us, algebra and symbol manipulation and algorithms are just tools that we use in the course of doing our jobs. And that job is to solve puzzles. It's like being a woodworker. People who work with wood better be able to drive a screw straight and to hammer a nail without hitting their thumb. They have to know how to use a bandsaw and a drill press. But using hammers and screwdrivers, saws and drills is not really what woodworking is about. Woodworkers don't get excited about pounding nails and driving screws. Rather, they get excited about the act of creation. Their skills in using those tools enables them to create interesting and useful things from wood. And so it is with mathematicians. What we care about is solving puzzles. All the trappings you hear about in math classes are just tools that we use towards that goal. So where do these puzzles come from? Well, sometimes they come from practical situations, and sometimes they don't. Sometimes they arise from real-world problems. Sometimes they're just idle diversions. But the most honest answer to the question of where mathematical puzzles come from is that we just make them up. Mathematicians go looking for trouble, and we have no trouble finding it. It's just as Demestre said, we create difficulties solely for the pleasure of resolving them. Let me give you some examples. Have a look at this clock face. Most people would see 4 o'clock and leave it at that. But a mathematician might wonder if it's possible to draw 2 straight lines across the face of the clock in such a way that the numbers in each of the sections all add up to the same thing. Of course, we'll assume that no number lies on the borderline of 2 regions to avoid any problems with ambiguity. Or consider a normal 8x8 chessboard. It would be very easy to cover the 64 squares of the board with dominoes, each of which covers 2 adjacent squares. But a mathematician might wonder if we could still cover the board with dominoes even after we remove the diagonally opposite corners, as you see on the screen. Or we might wonder how many chess knights can be placed on the board so that no knight can move to any square occupied by any other knight. Remember that knights move in an L shape like this. Think about that one for a moment. You have as many knights to work with as you like. What would be the best way to arrange them so that none of them can move to a square occupied by another knight? Of course, you can try random trial and error to get a feel for what's going on, but maybe there's a pattern to the knight's move that we can take advantage of. Or maybe the year is 1736, and you live in the city of Königsberg in what was then Prussia, but in what is today part of Russia. The city is crisscrossed by the Pregel River, which divides the city into 2 large islands and 2 mainland sections. These regions are connected by a series of 7 bridges. Now, if this is where you live, and if you spent a lot of time walking across these bridges, you might start to wonder if it's possible to do a single, continuous walk around the city in such a way that you cross all of the bridges, but you use each bridge once and only once. Why would you ask such questions? For the same reason mountain climbers climb mountains, because they're there. It's because once these questions occur to you, it's impossible to shake them until they're answered. But that's not the only reason. It's true that mathematicians view puzzle solving as a worthwhile activity in its own right. But we also know our history, and that history tells us that discoveries of fundamental importance routinely arise from the earnest contemplation of seemingly trivial pursuits. The great science fiction writer Isaac Asimov once said that great moments in science occur not when an eccentric genius suddenly yells, "Eureka!" Rather, they occur when someone involved in normal daily work sees something weird and says, "That's funny." He could as easily have been talking about math. Take the problem about the bridges in Königsberg. This problem was first considered by the great mathematician Leonhard Euler. His solution was to devise an abstract mathematical model in which the 4 land masses were represented by dots and the 7 bridges were represented by lines connecting them. In studying this model, he noticed something interesting. If during your walk you arrive on a particular landmass, you must subsequently leave that landmass as well. That means every time you cross a bridge to arrive on a mass, there must be some other bridge available to you for leaving that mass. The starting and ending points of the walk are an exception to this, of course. But other than the starting and ending landmasses, we see that every time we visit a landmass, we will use up 2 crossings, 1 for arrival and 1 for departure. Why is that significant? Because it means that for our walk to be possible, it must be the case that, at most, only 2 landmasses have an odd number of bridges connected to them, while the remaining landmasses must have an even number of bridges connected to them. But look again at our diagram. Every landmass is connected to an odd number of bridges. 3 of the landmasses have 3 bridges connected to them, while the remaining landmass has 5 bridges connected to it. We see, therefore, that the desired walk is not possible. Now, Euler might have seen this as just an amusing diversion. He was a very curious person who pondered the deepest mathematical and scientific problems of his time, and I picture him tossing this off in one of his lighter moods. But by solving the problem in the way he did, he inaugurated a whole new branch of mathematics. Today, we refer to the sort of diagram Euler pioneered, with dots and lines, as a graph. And the branch of mathematics devoted to studying such diagrams is called graph theory. And once someone has had the idea of studying a graph, you begin to see graphs everywhere. Maybe the dots represent cities and the lines represent airplane routes between them. Or maybe the lines represent communications channels between the cities. Or maybe we're modeling the internet, and we think of the dots as representing websites and the lines as representing links between them. Or maybe you're a biologist studying animal migration patterns. The dots can represent land areas where various species live, and the lines represent their migration routes. We can multiply examples all day. Once the idea of using a graph has been broached, everyone else rushes in to make use of it. And all because Euler got curious about a question of no practical importance, just because he found it interesting. Graphs provide a nearly bottomless pit of intriguing questions for mathematicians to ponder. Incidentally, a walk through a graph in which every edge is crossed exactly once is today referred to as an Eulerian walk. You know you've achieved something great in mathematics when your name gets turned into an adjective. Here's another example. The Chevalier de Marais was a French writer and gambler. He posed a version of the following problem to his friend, the mathematician Blaise Pascal. Imagine that Alice and Bob play a game in which the winner is the first to win 10 points. We assume that each player has contributed equally to the prize fund, and the winner keeps all the money. Now, suppose the game is interrupted at a moment when Alice leads by 8-7. What is a fair way of dividing the prize money? Of course, this is not purely a math problem, since some notion of fairness must be brought to the mix. But we can certainly take it for granted that the division should have something to do with who was closer to winning at the time of the interruption. Now, Pascal discussed this problem in correspondence with another great mathematician of his time, Pierre de Fermat. They hit upon the following insight. The game will definitely end in no more than 4 more rounds, since at that point, either Alice will have won 2 more rounds or Bob will have won 3. With 2 possible results for each round, either Alice wins or Bob wins, that makes 16 possible ways for 4 more rounds to be played out. Of course, in many of those ways, a winner will be found before all 4 rounds are played, but it does no harm to assume the additional rounds were played anyway. Now, we can list the 16 possible outcomes like this. And when we examine the list, we can see that Alice wins in 11 of them, while Bob wins in 5. So what's the fair way of distributing the money when the game is interrupted at the score of 8-7? Well, from our list of possible outcomes, we find that Alice should get 11/16 of the prize money, while Bob gets 5/16. Pascal and Fermat's solution was based on the idea that the person who was more likely to win the game should get the majority of the money, and that the problem of deciding this likelihood was ultimately a problem in counting. It was from such ideas that the modern theory of probability was born. One of the most important branches of modern mathematics arose from a puzzle about gambling. But there's a further point to take away from all this. What constitutes solving a problem? Imagine a modern computer scientist hearing for the first time about the bridges of Königsberg problem. He would probably say, we can just program a computer to try every possibility. It will certainly find the desired walk if it exists, or prove by exhaustion that there is no such walk. Problem solved. Well, maybe. That approach certainly answers the immediate question. But a mathematician would not be satisfied with this. For us, the goal is never just to answer the question. We also want to understand what is going on. The computer certainly gives us an answer, but it gives us no insight into why the answer is what it is. Contrast that with Euler's approach. He realized not simply that there's no walk through the city that uses every bridge exactly once, but he also found a concrete reason for why this is so. The issue is the evenness and oddness of the number of bridges connecting with each land mass, what mathematicians refer to as the parity of the number of bridges. That is, rather than just answer the immediate question, he discovered a general principle that works on any graph. The computer approach would have treated each such question as a new problem, entirely unrelated to anything that came before. and it doesn't take long for the graphs to become large enough to defeat even the most powerful modern computers. We could make a similar point about the correspondence between Pascal and Fermat. The solution I gave applied to a situation where the score was 8-7 in a game of 10, but would we have done anything differently had the score been 18-17 in a game to 20? Or 98-97 in a game to 100? What Pascal and Fermat wanted was not just the solution for a specific game with a specific score. Rather, they wanted general principles that could be applied to any game with any score. That, too, is part of doing mathematics. Once a specific question has been answered, we seek to generalize it to related problems. We don't want to reinvent the wheel every time. To a mathematician, the solution to a problem is never just an answer to the immediate question. It's rather a quest to understand, in as much generality as possible, the principles underlying the answer. And that is what we'll learn throughout this course. We'll encounter many stimulating and amazing puzzles. Some of these puzzles will yield to a moment's thought and a one-line solution. Others will require far more careful consideration and patience. We offer these puzzles partly because they're fun, and partly because they're illustrative of mathematical thinking more generally. But over and above all of that, we offer them in the conviction that everyone can benefit from the habits of mind they cultivate. There's ample research showing the brain is like a muscle. It gets stronger with exercise. Just as lifting weights can strengthen your muscles, so too can solving puzzles make you a better and clearer thinker. We'll focus especially on puzzles in pure logic, but we'll also discuss aspects of probability theory, arithmetic, and algorithmic thinking. Throughout, you will not only get to enjoy some clever puzzles, but will also develop habits of mind that are useful in everyday problem solving. It'll be a fun and exciting ride. Now, back to our earlier puzzles, starting with the hourglass problem. The puzzle was to time an interval of 9 minutes using a 4-minute hourglass and a 7-minute hourglass. If you haven't figured it out already, put the video on pause and see if you can solve it. Then return for the solution whenever you're ready. Did you figure it out? Well, here's how it's done. We start by turning over both glasses. Okay. After 4 minutes, the 4-minute glass will be empty, while the 7-minute glass will have 3 minutes left. At this point, you flip over the 4-minute glass again. After 3 more minutes, the 7-minute glass will be empty. The 4-minute glass will have 1 minute of sand left. And at this moment, 7 minutes have elapsed. Now, flip over the 7-minute glass. 1 minute later, the 4-minute glass will be empty, while the 7-minute glass now has 1 minute of sand in its base. 8 minutes have now elapsed. Okay? Now flip the 7-minute glass over one more time, and after 1 more minute, it will be empty again. That makes 9 minutes. The next puzzle involved my friend Steve, the waiter. He was serving a group of 4 people, and he asked them, "Do you all want coffee?" The first person said, "I don't know." Then the second person said, "I don't know." Then the third person said, "I don't know." And finally, the fourth person said, "No." Can you determine who wanted coffee and who didn't? Pause the video here if you want some more time to think this over. If you haven't given this one a try yet, I think you might enjoy having a go at it. So, how did Steve know who wanted coffee? Well, if the first person didn't want coffee, then he would have known that not everyone wanted coffee and would have said no. Since he didn't say that, it must be that he actually wants coffee. Likewise for the second and third diners. But the fourth person did know that not everyone wanted coffee, and therefore it must be that he didn't want any. So the answer is that the first 3 diners wanted coffee, while the fourth did not. Let's try the biased coin problem. 2 roommates are arguing over who has to clean the kitchen. They decide to flip a coin, but the only coin they have comes up heads 60% of the time and tails 40% of the time. How can they use the biased coin so that each has a 50-50 chance of having to clean the kitchen? As always, pause the video here if you want to think this over some more. This one really seems hopeless until you notice an interesting fact. Suppose we flip the coin twice. Then the probability of getting heads first, then tails, is the same as the probability of getting tails first, then heads. Think about it like this. We have a 60% chance of getting heads on the first toss, and then a 40% chance of getting tails on the second. Now, 60% is the same as 60 out of 100, which is 3 out of 5. And 40% is 40 out of 100, which is 2 out of 5. So the probability of getting heads first, then tails, is 3/5 times 2/5, which is 6/25. But on the other hand, we have a 40% chance of getting tails on the first toss, and then a 60% chance of getting heads on the second. Reasoning as before, the probability of getting tails first, then heads, will be 2/5 times 3/5, leading to the same 6/25 answer as before. And now we see how the roommates can solve their problem. One of them will flip the coin twice. The other will call out heads tails or tails heads. Each of these two outcomes is equally likely, meaning that each has the same chance of being the one to clean the kitchen. Of course, if we end up with heads heads or tails tails, then they can simply try again. Now let's do the clock problem. We were challenged to draw 2 straight lines across the clock face so that the sum of the numbers in each section was always the same. Now, you know the drill already. Put me on pause and see if you can solve this one. Okay. The key observation is that it is not possible for the 2 lines to form an X on the face. If they did, the numbers would be divided into 4 sections. Since the sum of the numbers in each section must be the same, all the numbers on the face would then have to add up to a number that's a multiple of 4. But actually, we have that 1 plus 2 plus 3 plus 4 all the way up to 12 is 78. And 78 is not a multiple of 4. That means that the 2 lines do not cross on the face, and therefore they will make 3 sections, not 4. And what must the sum of the numbers in each section be? Well, that's going to be 78 divided by 3, which is 26. Moreover, 2 of the sections will feature consecutive numbers. So, to solve the puzzle, we need to find consecutive numbers on the face that sum to 26. That dramatically limits the number of possibilities and quickly leads you to this solution. Some quick addition will show that 11 plus 12 plus 1 plus 2 is 26, and the other 2 sections of the clock also sum to 26. Problem solved. That just leaves us with the chessboard problems. We first asked whether it's possible to cover a chessboard with dominoes after we have removed the diagonally opposite corners. And then we wondered how many knights can we place on a chessboard so that no knight can move to a square occupied by another. If you'd like, you can pause now to work through both of these puzzles. Okay, the first chessboard problem is an absolutely classic puzzle. So if you've never seen it before, it's definitely one to remember. Notice that every domino covers 1 dark square and 1 light square. That means that when we've completely covered the board, the number of dark squares that are covered must be exactly equal to the number of light squares that are covered. But the diagonally opposite corners were both light squares. That leaves 32 dark squares, but only 30 light squares. So it's not possible to cover the board with dominoes. Which brings us to the knights. How many knights can we place on a chessboard so that no knight can move to a square occupied by another? Well, this time you have to notice that a knight always moves to a square opposite in color to the one it's standing on. If they're standing on a light square, they must move to a dark square. And if they're standing on a dark square, then they must move to a light square. That means we can place all of the knights on squares of the same color, but none will be able to move to a square occupied by another. And that makes 32 knights. And I hope these solutions illustrate my earlier point. There's something engrossing about a good puzzle. It's enormously satisfying to bring light to darkness, just by using the power of your mind. Flexible, creative thinking is useful in all aspects of life, and mathematical brain teasers and logic puzzles are a great way to develop good mental habits. We'll see a great many examples of this as we go along. See you next time.